matter to determine their interaction. And definitely the result was what we get, the output that we get out of that, it's not created on its own. Okay, we have to imply or we have to input the concept of this radiation energy to this. It's much more of physics, we can say. Much more simpler version. But when we say next, we spectrometry, it's the application of spectroscopy so that there are quantifiable results that can be assessed. That means one is a mechanical one, isn't it? And another one, that means when we say spectrometry, it is much more quantitative. So when we are about to implement this technique in life sciences, in any field of life sciences, when we are collaborating any of our work, our research work with this particular technique, it would be spectrometry, isn't it? Because most of the time we work with or we have this notion to quantify, like if I talk about protein quantification, so definitely we have to go for this spectrometric study. Okay? And we all know that mass spectrometry is a very powerful and analytical tool with high sensitivity and high mass accuracy, which is very, very important. And when we talk about the recent technical innovations in mass spectrometry, these techniques that have contributed to a range of highly sensitive and versatile instruments for high throughput, high sensitive and protein scale refining. Definitely we always think of mass spectrometry. Okay, so definitely spectrometry. Is it or not? Come on. Give me a big yes in the chat box. Okay. Okay, that's great. Now, so coming to the mass spectrometry experiment. So we all know that mass spectrometer, it comprises of some basic components. Because when we talk about the technique, it should comprise of some basic units or basic components, isn't it? So which are definitely much essential for that technique to be a successful one. Inside the mass analyzer, we have to come out with that. What are the charge compositions of that particular compound? So we know butane. Simultaneously. Okay. So that means if any compound is unknown to us, we want to deduce the particular charge status of that particular compound, then definitely we have to go for this experimental type, isn't it? And for that we need a mass spectrometric study. So supposedly butane, we know it comprises of positive charges. Okay. So definitely what will it do is, we will be placing this particular compound inside a mass analyzer, but we do not know that it is butane on a prior basis. We have to find out what particular substance is this. So what will the mass spectrometric do at first? And it will analyze the charges. And here we'll get to see that only positive charges is coming out. So at first end we will be able to note that, okay, this is a positive charged compound, or it comprises of both the charges. Okay. Another most important thing is that when we are separating inside a mass spectrometer, okay, what happens? we get some radicals. So the symbols which we use is, suppose if this is, I write X here, so it can be X positive, X negative, and there will be radical symbol. Okay, so radicals are also going to separate out inside a mass spectrometer, but it is not counted. Like when I'll finally get my data out of that, the radicals won't be getting mapped up. Okay, so only the core charged particles we are going to get as a data out of a mass analyzer. Okay, so here will be an ionizer. There will be a stream of gas phase molecules, molecular ions, and the most important thing that happens inside it is the fragmentation. Okay, the charge gets broken down. Okay, I'll be giving you some insight more on this, and there will be a detector that will be able to detect the type of the ions. Okay, now most importantly, the types of MS or mass spectrometric we have, that is very, very important to get analyzed, isn't it? So what are the types we have? We have accelerator mass spectroscopy, we have gas chromatography, we have liquid chromatography, we have inductively coupled plasma mass spectroscopy, isotope ratio spectroscopy, mass spectroscopy, ion mobility spectroscopy, tandem and thermal ionization mass spectroscopy. Not only this, we have a lot more. Okay, like another one, the most important one, we know that we have MALDI-TOF, matrix assisted laser desorption ionization time of light, which is a commonly used MS technique. And MALDI, we all know it's a soft ionization technique to create ions, okay, with minimal fragmentation by using a laser energy in TOF. Okay, and the protonated ions are accelerated by an electric field over there. Okay, so the velocity of the ion, it depends always on M/Z ratio. We have, apart from this, we have triple quadruple mass spectrometry. Okay, that is we call as TQMS. And triple quadruple mass spectrometer is a tandem mass spectrometer only. Okay, so definitely in which the first and third quadruples, they act as mass filters, and the second, it acts as a collision cell to fragment the selected precursors. So I'll give you a small insight on the mechanism here. Okay, so I'll take this blank portion. So what happens generally when we give in, suppose I have given the particular compound like CH3, CH2, CH2 like this. Okay, so is it, as I told you, it's a positive charged, if I consider to be as a positive charge, so it's an arbitrary compound I have taken. So as I told you, inside a fragmentation is going to take place. Okay, so how will it break down is like CH3, CH2. Okay, from the CH3, CH2, I'll get, suppose, CH3, CH like this. Again, it will break down to form CH3. So this is the way the fragmentation basically take place inside the mass analyzer. Okay, and what happens now, as I was talking about the M/Z ratio. So suppose if I consider that the molecular weight of this particular compound is 58 gram per mole, then the first M/Z amount that we are going to get, it should be always lower than the exact molecular weight. Okay, so if suppose I got the first M/Z ratio to be as 45, so I am going correct. I have no anomalies in that particular process. Okay, so that is my first thing to be, we have to consider that. Okay, so suppose that means CH3, CH2 will have an M/Z ratio for arbitrarily it's 45. Next, we'll move on to CH3CH, suppose. So definitely it will have a lesser M/Z ratio, suppose it will have 30, suppose. Okay, and CH3 will have got 15. So like this, no, it will be degrading. The fragmentation will take place like this. Clear? And ultimately, no, these all are called as fragmented ions. Whatever ions we are going to get in between, they will be all referred to as fragmented ions. Okay, and finally the ones which we are going to get, that means ultimately we will be getting only carbon also. So if this status will be called as product ions or the daughter ions, because that is the final fragmented ion we are getting. Okay, so it can be called as a daughter or a fragmented ion. So this is the entire rough procedure I told you about this. And more or less For all the types of mass spectrometric techniques, the same concept or the principle will be followed. Okay, so be it for your thermal ionization, be it for anything, but sometimes what happens, like it is like when we cook anything, the principle is same. You have to lit your oven, you have to give and put an oil to that, but this is the basic thing, right? But for different dishes, you have to give in or put in different spices, and then only it will create separate dishes. So same goes for mass spectrometry here. The concept, the principle remains the same. But when it is for different categories like gas, like liquid chromatography, like isotope ratio mass spectroscopy, IRMS, or if I talk about hybrid linear ion trap, orbit trap mass spectrometry, all these things, they have some different components that are used. Okay, there lies the difference between all these different techniques. Okay, like I told you about hybrid linear ion trap. Okay, it's called as another technique, hybrid linear ion trap. Okay, so this is another technique. So in this, what happens, this MS, it combines a linear ion trap and high resolution orbit trap, which is one of the tandem mass spectrometers. Okay, and the orbit trap, it consists of an axially symmetrical mass analyzer that make the ions in an orbital motion around the spindle. So these are all high definition mass spectrometers, okay, and they definitely are very, very costly also. But yes, the precision which you get is excellent, okay, the excellent precision you will be getting with these techniques. So applications of mass spectrometry. So what are the applications? Yes, definitely we have to know that, okay. So first and foremost, how MS has been contributed to healthcare. Okay, it has got a great contribution. So yes, if you look at MS-based metabolomics, in health and medical sciences, okay, then we have applications in the field of precision medicine, forensic sciences, toxicology, nutrition science, drug. So a lot of fields we'll get to see the amalgamation of mass spectrometry is taking place. So definitely it has, mass spectrometry has gained a lot of popularity for protein analysis, and it is highly on demand. Like for protein analysis only, it is highly in demand, specifically in the healthcare sector. Okay, and definitely for protein analysis, due to its ability to tackle the intricacies underlying the proteome. And the most important thing is the three fundamental applications of the technique in proteomics, which is based on mass spectrometry, will be the protein interactions. Number one will be protein interaction. Number two will be categorizing protein expression. Okay, so I'm writing in short. And the third one will be locating sites of protein modification. So these are the three pillars, I would say, upon which the entire application of mass spectrometry is dependent. Okay, so for this, it has really gained a lot of popularity in the field of healthcare sector. Now, when we come to proteomics, it is definitely very, very important. So in case of proteomics, how it is important basically. So analysis of the entire protein complement of a cell, tissue or organism under specific defined set of conditions. Okay, like definitely mass spectrometry already has emerged as an indispensable method, okay, for the characterization and sequencing of different proteins, and the development of specifically the two soft ionization techniques, that is electrospray ionization and matrix assisted laser desorption ionization, these two, ESI and MALDI. They have revolutionized protein analysis, I would say, via mass spectrometry. Okay, so it's really very interesting that we have, or we are able to amalgamate and collaborate the technique of mass spectrometry with the field of proteomics. And it's a great technique, I would say. So as I told, it relies on three basic technologies.